You say Steve, my friend?
Yeah, so I don't know, for this talk, I just kind of wanted to go a little bit into like something that I just quite like. So I've always been interested in astrophysics. Something I find really interesting is in science, a lot of the times, looking at how we actually know things, it can be really interesting to like actually delve into the actual process that we use to find something out. And sometimes it's a bit ridiculous. So like, if we just think about this question of where are the stars, and like more specifically, how do we know where the stars are? I don't know, that it's kind of crazy that we can find out where these dots of light in the sky actually are, especially as you get further and further out. And like actually how far out we can like measure distances becomes pretty impressive. So I'm kind of going to go through like a fairly high level thing of how we know essentially how far where different stars and galaxies are. And then I'm just going to open to questions because it's going to be pretty high level just to give you an overview of how this happens. So yeah, we're going to pick a star. That kind of works on this screen. Yeah, that might work. And that's going to be our example. And yeah, we're going to look at like what do we know about this star. We have some information about brightness, but it's brightness from Earth. We have information about position. We can see it move, and we can kind of look at color. So brightness, we kind of can't tell the difference between a star that is close and dim or far and really bright, because if it's far away, like just because of the way distance works, they will look actually the same in the night sky for most purposes. So that's like quite not very useful at this stage. Color, like basically all stars look white. So yeah, we can delve into this a bit more, but at the start, they don't look that much more than that. Position, like the position's moving pretty fast, so it moves across the sky every night, and then how it moves across the sky changes every day, so that's a bit of a mess. And movement, and that's kind of where we get to movement. And like movement, a lot of the movement here is based on the rotation of the Earth and the movement of the Earth around the sun. So just say we take out the rotation of the Earth, so we only look at this at midnight, say, and we're looking at it from the equator, so we're right in the middle, or we do some maths to fix that. Then what we see is like as the Earth moves around the sun, the star appears to move the other way, essentially. So it's in a slightly different position. We can then correct for that by either, again, doing some more maths, or you could essentially only look at certain points in the orbit, certain times of year, and you're going to get a position of the star. So yeah, we can correct for this orbit, essentially. And so you do all that, and we essentially get to a stage where we know it's somewhere on this line. Here's the Earth and the sun. There's a line coming out, and somewhere on this line is this star. And we can figure that out pretty quickly for all of them. But where on that line, basically the rest of this talk is all about distance, because distance is the hard bit. The universe essentially looks like a flat 2D plane to us, or actually the inside of a sphere. But it obviously has depth. And so how do we find that depth? If the star is close, there's a cool thing we can do called parallax. So basically, the way we can tell distance with our eyes normally is there's a distance between our two eyes, and so an object looks slightly different from your left and right eye. And your brain computes that automatically to figure out how far away it is. So we can do something slightly similar where we use the orbit of the sun to create two different points. So we look at it once when we're, I don't know, in January and another time in July, and we can see there's a difference in where the object is. And so there'll be a little angle essentially involved, and then you can calculate the distance. This is not to scale. It's a little bit more accurate, but it's still not to scale. The closest star is Proxima Centauri, and this is the angle that it makes. It's 2 centimeters on one side to 5.3 kilometers is the angle that we're talking about here. And that's the closest one, so it's ridiculous. What's impressive is that there's a limit to how much we can actually go out into the universe because the angles get smaller and smaller. So basically, we can do this to a certain distance. At first, we were limited by the fact that essentially any light that comes through the Earth's atmosphere gets a certain amount of fuzz added to it because of the atmosphere. And so there's a hard limit for how far away you can figure out parallax because of that. Then we send some stuff out into space, so we have some satellites in space that do a better job. But this is basically what we can see. So we can see about 1,600 light years in any direction and figure out distances pretty well in that case. The galaxy is 100,000 to 180,000 light years across. So it's really not far. It's about 1% or so. Yeah, something I was futzing around with stellar data a while back. With data about stars that we can see with the human eye, I realized that you can very easily tell the difference between if you're looking at the data for above and below the galactic plane, which is why we can see the Milky Way, and that's great. But there is zero way to tell whether we're facing towards the middle of the galaxy or away, towards the edge. There's just not enough information. We have no idea based on what you can see with the human eye. You have to be looking at with telescopes and that sort of thing to get that information. And it just gave me an idea of how big it is. Yeah, and this is another one. 1,600 light years is well past what a human eye can see as well. So yeah, what we have here is then what's called a distance, I think it's the astronomical distance ladder. But it's a ladder where we can start using what we know to then find out more, essentially. So at the bottom of this ladder is parallax. It's used for the really close things, and it's really quite accurate. We're pretty happy with it. As we go, we then have to build more and more models on top of each other to try and find higher and higher distances. And what ends up happening is these methods all start depending on each other. So there'll be something where someone realizes that one of them is slightly wrong, and then all the distances change a bit. Yeah. So this is, what we can do next is we actually use color. So color, all stars look bright, but you can actually look at their spectra and they have different characteristics. So there's stars that are blue up here, which are the really hot ones, and then white, yellow, and red. So the red ones are actually the coolest stars and the blue ones are the hottest. And what you find is if you chart all the other thing you can find out is if you know the actual distance of the star and you can see how bright it is from Earth, you can figure out how bright it is in the absolute sense. Because you can essentially work out, if you were at a shorter distance, how bright it would be. So what we can do then is we can actually chart these. So if we chart all of these, what we find is there's this main sequence of stars that basically is, and we're charting the absolute magnitude versus the color. And so you can kind of get, if it's a normal star, basically you're going to get it on that line. And so if you figure out the color of another star, you can figure out essentially where it is. And there's quite a lot of fuzz to this. It's not a perfect match. And then you've also got to realize that there are other lines going on for giants, and these are the white dwarfs. Red dwarf? White dwarfs. And so on and so forth. So you've got to be a little bit careful, and you've got to make sure that you're looking at the right type of star, but you can get some sort of idea. So that becomes our next rung on the ladder, the main sequence fitting. And that works, but it's not 100%. What we can then do, from here there's basically a bunch of statistical things. So there's 20 of these, but I'm just going to show you 3 of them just to give you an idea of what sort of things astronomers are using. So this is Cepheid Variable. So these are stars that blink, essentially, or change in brightness over time. And a specific type of them where they found that there's a correlation between how fast they're blinking and how bright they are. So the faster they're blinking, the brighter they are, I think it is. And so if you see one of these things and then you check how fast it's blinking, you can figure out how bright it is and therefore distance. It's quite easy to work out from there. And they're pretty reliable. Another one is looking even further at...
What causes the blinking?
Oh, I haven't looked into that. Yeah, that's a good question. It's often things like... So it could be I don't know specifically for those types of stars, but blinking could be things like moving around another star. It could be It's probably something around the chemical reaction happening inside the star that's varying over time. It would be my guess, but I'd have to look into it. So yeah, if we look even closer at color, what we actually see, so at some point, people in chemistry were like looking around at different elements and realized that if you get different elements to essentially emit light in different ways, they emit very specific wavelengths of light. It's really clear, really specific. And so if we look at stars have a fairly specific spectrum overall, and then they have parts that deviate from that, like bits that go, parts of the spectrum that are really, really bright, and parts that are a bit darker. And you can use that to figure out basically what the makeup of the star is. And so, yeah, we've got hydrogen, helium, lithium, beryllium, et cetera, et cetera. And so a scientist can look at a star and find these lines and see what the makeup of the star is. And it's been shown fairly well that if you find two stars that basically have the same spectra, that they're basically the same star. They'll have the same brightness. And so again, you can figure that out. This isn't an amazing method. There are some doubts about it, and you have to have a pretty good match. So it's not as useful as some other ones. The other one is clusters. So there's lots of clusters of stars in the universe that are just like a bunch of stars that are all born around the same time. So they'll have like similar properties. We know that they're all near each other just because of that they'll be orbiting each other and that sort of thing. So we can actually figure out some of this stuff. And then you can do some statistical analysis on it as a whole and find out things that you couldn't find out for an individual star. And so that's another thing that people use. Finally, supernovae. Supernovae are like the best, one of the best ones, because they go really, you can go really far with these. Actually, so one specific type of supernova is one of the furthest distance candles that we have. And so in this case, yeah, so the type 1a supernova is the really, really nice one. And it's because this supernova happens when a star turns into a black hole. And that happens at a very specific mass, and it doesn't happen at any other point. And so we know the exact mass of the star, so they actually have the same peak brightness. So if we see the entire thing, the entire explosion, we can see where the peak brightness is, we therefore can figure out where it is. At this stage, we're actually measuring galaxies. So some of these happen inside our own galaxy, but mostly when we're talking about supernova, and Cepheid variables are fairly similar, we're often talking about other galaxies and how far away they are. So yeah, that gets us most of the way. There's lots of other things in that mix that are, again, mostly just like, let's look at a bunch of stars that we know the distance and the magnitudes of. Let's do some statistics and try to figure out what we can find that will tell us something about something else. Yeah, and actually fairly recently, there was a correction made to the type 1a supernova distance count. There was a correction. I think they realized that there were actually two categories, not one. And that changed how they thought about where things were. Okay, so finally, we have parallax. So this is the Doppler effect, essentially. So we have a car that's going past us. As it goes past, it goes, wee-oo. And the wavelength changes as it goes past, right? And this is something we see all the time. And basically, that's because it's going at a different velocity than we are. Something very similar happens with the emission spectra. So if we have two stars, if one's coming towards us, all those lines that we know exactly where they are will be a little bit more blue. And if something that's going away, everything will be a little bit more red. And we can measure that and figure out how fast it's going, how fast it's traveling. That's towards and away us velocity, not across the sky. So that gives us a velocity, but that's not super useful. It turns out actually to be kind of a pain that this happens, because the actual thing that's useful in terms of doing distances, and this is like the really long, far away stuff, and it only works for the far away stuff, is that the universe is expanding. So we, through a lot of other observations, have figured out, and through general relativity and a whole lot of other things, figured out that the universe is expanding. But it's not just that things are moving away from each other. The actual space between all the things is getting bigger. So that means everything gets further away uniformly. it also means that light that comes towards us actually gets stretched. So blue light that comes towards us, if it comes from far enough away, it actually gets stretched on the way through as the space that it's in is being stretched. What this means is that, and it's being stretched at a uniform rate. So we actually know how fast this happens. So if we look at the wavelength of one of those hydrogen lines, and it's like this much more red, then we can be pretty sure that that's a certain distance away because we know how much it stretches over time. And this is all based on a single constant. So like, again, if that constant changes and there's still uncertainty over that, then all these distances change. So yeah, and that's cosmological redshift. And that's really our highest thing. And that's kind of nice in that we've got all these like fairly statistics things going on. And then at the top, we just have this nice like, oh yeah, just like measure this number and like divide. And it's a really simple measure comparatively. Cosmological redshift only works for things far away because of normal red and blue shift. Because if it's too close, then what you're seeing could be it moving towards and away from you. But nothing moves fast enough to like account for cosmological redshift. So we can be pretty sure as it gets further and further away what it is. That's basically it.